Hello everyone and welcome. In today's video, we are going to be approximating areas under curves. And to do that, we will create rectangles. And what if we just add up the area of these rectangles, and that can give us an approximation to the area underneath the curve. And the more rectangles we have, the better the approximation. So to that end, let n be the number of rectangles. And let's suppose we want to find the area underneath the function over the interval from a to b. So we will begin by partitioning the given interval into n subintervals of equal width. So how can I break this interval up into n equal chunks? Well, simply take the length of the interval, b minus a, and divide it by how many rectangles I want, n. And so that means each rectangle should have a width delta x, which is going to be this constant fixed number. Okay, so in terms of the diagram, what we have done is we've taken our interval and we split it into n subintervals. So we have the first interval, which is right here, second interval, which is right here, third interval, which is right here. And all of these intervals have width delta x. So the width of the rectangle is already defined. The width of these rectangles are each delta x. The question is, what is the height? And here is where we get different types of approximations. So let's first take a look at right endpoint approximations. What this means is that to define the height of the rectangle, we will have to use the right endpoint's function value. That's how big the rectangle is going to be. Similarly, to define the height of the second rectangle, we will have to use the function value of the right endpoint. So we have to evaluate f of x2, and that will give us the height. And so that's really all there is to right endpoint approximations. The width is always going to be delta x, and then the height of the rectangle is defined using the right endpoint of that subinterval. We evaluate the function at xi, where xi is the right endpoint. So now the question is, how do we find these right endpoints? Because we need to know these x values so that we can compute the output at these x values. And there's a very nice intuitive formula for this. The right endpoints of the subintervals are given by this formula. We simply have to take a, which is the starting number, and then you just have to go multiples of delta x, right? 1 delta x puts us here, 2 delta x puts us here, 3 delta x puts us here, and that's how you generate the right endpoints. Here, I can run from 1 through n. When you plug in 1, you will get x1. When you plug in 2, you will get x2. When you plug in I equals 3, you'll get x3. And all the way to the very last right endpoint, the very last right endpoint would be xn. So you just plug in n, and that means you have to go n multiples of delta x, which is your fixed width. And so now to get our approximation, we simply have to add up the area of each rectangle. What's the area of a rectangle? Height times width. Well, the height of the first rectangle is given by f of x1. What's the width? Delta x. So that's where you get this expression. Plus the area of the second rectangle. What's the area of the second rectangle? Well, its height is f of x2, right? The function evaluated at the right endpoint of this subinterval. And what's the width? Delta x. That's where this comes from. And we keep doing this. We add up the area of the third rectangle, the area of the fourth rectangle, all the way up to the very last rectangle, whose area is going to be given by height times width. The height is going to be the function evaluated at the right endpoint of the last subinterval. And the last subinterval has right endpoint xn, so that's the height. And the width is fixed, delta x. And the notation we use to define this is Rn. So Rn just stands for the right endpoint approximation using n rectangles. Now, since the widths are just constants, you can just factor it out, right? Delta x is common, just factor it out. And so you end up with this expression, delta x multiplied by the sum of all the heights. And using sigma notation, which is a compact way of representing sums, we can rewrite this sum as simply the sum starting from I equals 1 to n of the terms f of xi. So the sigma symbol over here just denotes sum, and then I is like a dummy variable. You can use whichever variable you want. You can use j, you can use k. And so when I is equal to 1, you get f of x1, which is this term. Plus, then you plug in I equals 2, which is going to be f of x2, which is this term. Plus, and then you plug in I equals 3, which is f of x3. Plus, and so on and so forth, all the way up to f of xn. So it generates exactly this expression. That's sort of how sigma notation works. And so this is the formula you want to remember for right endpoint approximations. Later, when we take a look at examples, you'll see the idea is very simple. We're just going to find the area of each rectangle, and then we're just going to add the numbers up. That's it. Next, let's take a look at left endpoint approximations. It turns out that there's nothing special about the right endpoints. To define the height of each rectangle, we could also use the function value evaluated at the left endpoint of each subinterval. So as you can see on this subinterval, we're creating a rectangle, but the height is defined by the function value at the left endpoint. That is what determines the height. Previously, we would have actually created the height like this. We would have used the right endpoint function value and made this larger rectangle. That's the difference. So now there will be a very slight modification in how we compute the left endpoints. The formula is the exact same. You have to take your starting value a and add multiples of the width. However, instead of starting from 1 and going all the way to n, we actually have to go from 0 to n minus 1, right? x0 represents a, that's the first left endpoint. And the last endpoint is not b. b is equal to xn. We don't want that one. That's actually the right endpoint of the last subinterval. We want xn minus 1. That is going to define the very last height of the last rectangle. Hence, we go to n minus 1. And so now we define the left endpoint approximation for the area under a curve. And it's very simple. It's just the area of each rectangle added up. What's the area of the first rectangle? Well, the width is delta x, and the height is given by f of x 0. So when I multiply the width and height, I get the area of the first rectangle. That's this expression. Plus, we have to add the area of the second rectangle. Well, the width is delta x, the height is f of x1. Multiply those together, that's how I get this expression. It just represents the height of the second rectangle. And we keep doing this all the way to the last rectangle, where its width is delta x, but its height is going to be f of xn minus 1. And so when you multiply them, you get exactly the height of the last rectangle. Now you can factor out the delta x because it's a constant, and then write it in sigma notation like this. And so this left endpoint approximation is very similar to the right endpoint approximation. The only difference is the indices. Instead of going from 1 to n, we're going from 0 to n minus 1, because we want to include the very first endpoint, and we don't want to include the last one, but the second last one. Whereas in the right endpoint approximation, we wanted to skip the very first number, hence we started from I equals 1, and we wanted to include the very last endpoint, which is at n. And lastly, let's talk about the midpoint approximation. In this case, instead of using the left endpoint or the right endpoint to define the heights of each rectangle, in this case, we are going to take the midpoint of each subinterval and use the function value at those midpoints to define the height. So as you can see for this very last rectangle, we're taking the midpoint, which is right over here, and evaluating the function at this midpoint, and that will define the height of this rectangle. Just to compare this with the previous two approximations, if we were using left endpoints, then we would just cut the rectangle off right there, because that would be the value of the function at the left endpoint. And if we were using right endpoints, then the height of the rectangle would be up here, because that is the value of the function evaluated at the right endpoint that would define the height. So those are the differences, as you can see, of the three rectangles. Now the question is, how do we find these midpoint values, right? Because this is where I need to evaluate my function to define the heights. So we need an expression to represent these midpoints. How do you find the middle of two numbers? Well, you take a simple average. You add the two numbers up, and then you divide by 2. And that number is guaranteed to be right in the middle, halfway between the two numbers. As a result, we will denote the midpoint of each interval as xi with this bar on top to represent the average of each interval. And it's very simple. Just take the left endpoint plus the right endpoint, add them up and divide by 2. And here, I runs from 0 all the way to n minus 1. There are also other ways to define this, like you can make this to be I minus 1 and then take this to be I. Then the range will just change from like 1 less than or equal to I less than or equal to n. Okay, so your textbook might have it a little bit different, but the idea is the same. The idea is that the height of each rectangle is defined using the function value of the midpoint of each subinterval. Now we have to add up the area of each rectangle. And so we call this the midpoint approximation. What is the area of the first rectangle? Well, the width is delta x, and the height is going to be given by f evaluated at the midpoint of this interval. What's the midpoint? Well, x is 0 plus x1 divided by 2. That's the number that lives right here. Right, x0 is just a, keep that in mind. And so that's why we have this expression here. It just represents the area of the first rectangle. Similarly, this represents the area of the second rectangle. The width is delta x, and then x1 plus x2 divided by 2 represents the number right in the middle over here. And so we're evaluating the function at this midpoint of the subinterval to define the height. And you keep doing this all the way to the very last rectangle. Again, delta x is constant, so you could factor it out from the sum. And you end up getting this final formula written compactly using sigma notation. And so there we go. We have covered left endpoint, right endpoint, and midpoint approximations. And the idea is that we're adding up the area of a bunch of rectangles. And how we define the heights of those rectangles, whether using the left endpoints or the right endpoints or the midpoints, is the difference between these approaches. And so now you might be wondering if there are other methods of defining the height of the rectangle other than just the left endpoint, the right endpoint, or the midpoint. And in fact, there is. What we're looking at here with the left endpoint, right endpoint, and midpoint approximations are something called Riemann sums. These are the special cases of Riemann sums. Riemann sums will generalize this idea. General Riemann sums let you pick any sample point within your subinterval. Now that sample point could be the left endpoint, the right endpoint, or the midpoint, or any other point, and then use the function value at this sample point to define the height of the rectangle. So again, we'll take a look at this in more detail in a future video. For now, let's just focus on left endpoint, right endpoint, and midpoint approximations to keep things simple. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.